The next characteristic of sound that we deal with is pitch. Pitch is related to the frequency of a wave. Now, the audible range of sound is between 20 hertz and 20,000 hertz. That means, on average, the lowest pitch that someone can hear is 20 hertz. So the lower sounds that are really deep. The lowest sounds that people can hear are right around 20 hertz. And now you guys are all dying to hear me do the upper range now too, aren't you? The really higher pitches, okay, I'm done. There we go. The higher pitches that people can hear can reach about 20,000 hertz. That's the upper limit. Now, again, this is average. The audible range varies from person to person, and it can the range can decrease with age as the muscles and the nerves get worn down over time. So, whereas some people may be able to hear pitches at 20,000 hertz, others won't. Generally, younger people can hear 20,000 hertz a little more readily than older people can. Now, when we talk about something being ultrasonic, that means that the frequency is above 20,000 hertz. Down here is a picture of a camera, which sends, in order to autofocus, it sends a small sound wave at a frequency higher than 20,000 hertz, so it's ultrasonic. It sends that sound wave to the object, which then reflects it back, which helps the camera know how far away the object is, so it can automatically focus to that distance. That's how autofocusing works, is using ultrasonic waves. Now you can use infrasonic waves as well, which are waves that have frequencies less than 20 hertz. Here's a website. I'm not going to do this here right now, but here's a website that you can go to, onlinetonegenerator.com, where they actually can produce sound waves. So if you would like to, you can go to this website and see if you can hear 20 hertz. So if you go to 20 hertz, you're going to want to put the volume of your computer up as high as it can. Go 20 hertz, 25 hertz, 30 hertz, 35 hertz, 40 hertz, so on, until you can hear that sound. See how low your audible range is. I don't recommend it, but you can see how high your audible range is too. If you do want to do that, then turn your volume on your computer way down. In fact, turn it to 0. Go to this website, the Online Tone Generator, set it to 20,000 hertz and play it, and then slowly increase the volume, see if you can hear it. Then set it back down to 0, decrease it down to 19,000 hertz, see if you can hear that. 18,000 hertz, see if you can hear that. If it bothers, it's not required, so don't feel obligated like you have to do it. Some people are sensitive to high sounds, so I understand that. So musical instruments produce sounds in a whole variety of ways. We can do vibrating strings, which is what we saw back in chapter 11. You have vibrating membranes, like what our ear does to register sound, or like a drum. Or you get vibrating metal or wood shapes, like brass or woodwind instruments. In these metal or wood shapes, you get vibrating air columns. And so you can induce the vibrating by plucking a string, striking a membrane, using a bow to vibrate a string, or blowing into a metal or wood tube. But whatever happens, as you do any of these, it induces a resonant wave into the string or the membrane or the wood or metal tube. And the vibrations then are transmitted through the air to our ears, and that's how we hear the sound from an instrument. So strings on a guitar, you can change the pitch quite readily. Remember that the speed of a wave is related to wavelength and frequency. Well, the speed of a wave, the wave's not going to change. But if you can shorten the wavelength, then you can increase the frequency or increase the pitch. So if you put your fingers somewhere on a string, you're going to decrease that wavelength. You can see that before the wavelength was the entire string, but now the wavelength is, well, excuse me, the wavelength was twice the entire string, and now it's twice only the shortened length in the bottom picture. You can also change the pitch by changing the tension or changing the string density of the string as well. Pianos, instead of using a device to shorten the length of one individual string, a piano just has multiple strings. And all of these different strings are made of different materials. They all have different tensions, and they're all at different lengths. And because of all of this, it allows all the different pitches. Now, wind instruments are a little bit different. What you're doing, instead of creating a vibrating wave in a string, you are actually creating a vibration in the air itself. So this is what it would look like. Here we're looking at a tube that is open at both ends. That's most wind instruments. You're talking about flutes and brass instruments, so on. What's happening is at the opening of the tube and at the closing of the tube, the air molecules are going to vibrate a lot. But if the molecules in the opening of the tube vibrate this way and the molecules in the end of the tube vibrate the other way, that kind of pushes all those molecules. They just stay in place in the middle, and so those molecules don't move. So if we plot the amount of movement of the air or the displacement of the air, we see a lot of movement here on the opening and on the two openings of the tube, and little to no movement at all in the middle. So we end up having an antinode on each end and a node in the middle. This is our fundamental frequency within a tube. This is the most basic frequency you can get. By the way, on the right, you're seeing pressure variations in the air. So basically, as the molecules on the two ends vibrate inward, it increases the pressure in the center. Whereas if the molecules at the openings vibrate outward, it decreases the pressure in the middle. And the pressure at the two openings is going to be relatively constant, and so you get nodes there. And so we get an inverse look. Not an inverse look, that's not a good way to say it. When you're looking at the displacement of air, you have an antinode on both sides with a node in the middle. But when you look at pressure variations in a tube, you get nodes on the ends and an antinode in the middle. Just for sake of consistency, we are only going to look at the displacement of air. Okay. That being said, this is our fundamental frequency, the most basic frequency we can have. You can see, let me grab a highlighter here, that one wave is only half, or the length of the tube is only half of a wavelength. And so as a result, your wavelength of your fundamental frequency is 2L. The second harmonic looks like this, and you do have a full wavelength there, so the length of the tube is equal to your wavelength. And the third harmonic, the third harmonic looks like this. It's a wavelength and a half, and so the wavelength of the third harmonic is 2L over 3. And perhaps you can see the pattern that's happening already here. I'm going to pause here, let you guys figure out what the pattern is, and we'll come back in the next video and see if we have identified it.